April 6, 1917, somewhere over the Western Front, a German Fokker D-7 banked sharply through scattered clouds, its pilot scanning for Allied reconnaissance aircraft. The sleek fighter's fuselage gleamed with an unusual metallic sheen, different from the fabric-covered planes that dominated the skies. Inside that airframe, a revolutionary material gave Germany an advantage that no Allied nation could match: Duralumin, an aluminum alloy stronger than mild steel, yet weighing 1/3 as much. 3,000 miles away in Pittsburgh, Pennsylvania, engineers at the Aluminum Company of America stared at metallurgical reports with growing alarm. American aircraft factories were preparing to build thousands of planes for the coming war effort, but they faced an impossible problem. Germany controlled the secret to aviation-grade aluminum. The formula for duralumin remained classified, locked away in German laboratories. American aluminum was soft, suitable for cookware and electrical wire, but utterly inadequate for aircraft that would face combat stresses at altitude. When the United States declared war on Germany that April morning, American aviation existed mostly on paper. The Army Air Service possessed fewer than 300 aircraft, most obsolete training machines. Congress had authorized 22,000 combat planes, but building them required materials America didn't have and couldn't produce. Not because aluminum ore was scarce. America had plenty of bauxite. Not because smelting capacity was insufficient. Alcoa operated massive facilities. The problem was metallurgical. American engineers didn't understand how German duralumin achieved its remarkable properties. This is the documented story of how an obscure metallurgist in New Kensington, Pennsylvania, discovered the secret to age-hardening aluminum. How his accidental breakthrough gave America a material that Germany thought it monopolized, and how that metallurgical innovation made possible the 300,000 aircraft America would produce to win World War II. The physics of flight impose merciless constraints on materials. Aircraft must be light enough to fly yet strong enough to survive. Every pound of structural weight means one less pound of fuel, weapons, or crew. The engineers who designed early aircraft understood this brutal calculus. Wood and fabric dominated early aviation because they offered acceptable strength at low weight. But wood splinters, fabric tears, both rot in moisture and burn readily. By 1910, visionary designers recognized that metal aircraft would eventually replace wooden ones. The challenge was finding metal light enough to fly. Pure aluminum seemed promising. Discovered in 1825 and first commercially produced in 1888, aluminum weighed about 1/3 as much as steel. But pure aluminum was soft, easily bent, structurally inadequate for aircraft frames. It worked fine for pots and pans, but would buckle under flight loads. Engineers needed an aluminum that behaved like steel but weighed like aluminum. In 1906, a German metallurgist named Alfred Wilm stumbled onto the solution while working at the Zentralstelle für wissenschaftlich-technische Untersuchungen in Berlin. Wilm was investigating aluminum alloys for the German military, seeking materials for airship frames. He experimented with adding small amounts of copper, magnesium, and manganese to aluminum. One day, preparing samples for hardness testing, he quenched some aluminum-copper alloy specimens in water after heating them to high temperature. Initial hardness measurements showed nothing remarkable. The samples remained soft. Wilm set them aside. Over a weekend. When he returned Monday morning and tested the same samples again, he found something extraordinary. The hardness had nearly doubled. Over the following days, it continued increasing. The aluminum had somehow hardened itself at room temperature without additional heat treatment. Wilm had discovered age hardening, though he didn't understand the mechanism. He only knew that his alloy, when properly heat treated, achieved strength approaching mild steel while weighing far less. Wilm patented his discovery in 1909. The Duraner Metallwerke licensed the patent and began commercial production, naming the alloy Duralumin, combining Duran with aluminum. By 1914, Duralumin was transforming German aviation. Zeppelin airships used Duralumin frames instead of aluminum, enabling larger, stronger dirigibles. When war began, German aircraft manufacturers adopted Duralumin for structural components. The Fokker and Junkers works produced increasingly sophisticated all-metal aircraft while Allied manufacturers remained stuck with wood and fabric. The Germans guarded their metallurgical advantage jealously. Duralumin composition was classified military intelligence. Export was forbidden. When the United States entered the war, American intelligence knew duralumin existed and understood its importance. They did not know how to make it. The man who would solve this problem was Raymond Harris, a 32-year-old metallurgist working in Alcoa's New Kensington Research Laboratory. Harris had joined Alcoa in 1911 after studying metallurgical engineering at Carnegie Technical Schools. His early work focused on aluminum electrical conductors, mundane applications far removed from aviation. But in April 1917, his supervisor handed him a new assignment. Find out what makes German duralumin work, reproduce it, do it fast. Harris began with the fragmentary intelligence available. Allied agents had obtained samples of duralumin from captured German equipment. Chemical analysis revealed the basic composition: approximately 95% aluminum, 4% copper, with traces of magnesium and manganese. American metallurgists could reproduce this composition easily, but when they did, the resulting alloy remained soft. It didn't age harden like German duralumin. The secret wasn't in the composition, it was in the processing. Harris spent weeks experimenting with heat treatment schedules. He tried different temperatures, different quenching media, different holding times. Progress came slowly. The laboratory's equipment was primitive by modern standards. Temperature control was imprecise. Sample preparation was laborious. Each test cycle consumed days. In June 1917, Harris was running yet another series of quenching experiments when equipment failure forced him to interrupt a test. He had heated samples to 500 degrees Celsius, preparing to quench them in water. But a laboratory accident required his attention elsewhere. He left the samples in the furnace, intending to return immediately. Emergency repairs took longer than expected. When Harris finally returned, the samples had cooled slowly in the furnace rather than being quenched rapidly. Disgusted with the wasted experiment, Harris nearly discarded the samples. But scientific habit made him test them anyway. The slowly cooled samples showed no hardening as expected, but something in the test results caught his attention. The samples quenched from slightly lower temperatures, around 480 degrees Celsius, showed different behavior than those quenched from higher temperatures. This observation led Harris down a different research path. He began mapping the relationship between solution temperature, quenching rate, and subsequent aging behavior. Over the following months, he discovered that duralumin's age hardening depended on precipitating microscopic copper-aluminum compounds within the aluminum matrix. The compounds formed only when copper atoms, dissolved in aluminum at high temperature, became supersaturated after quenching and then slowly precipitated at room temperature. The process required precise control. Heat too high and grain growth weakened the material. Heat too low and insufficient copper dissolved. Quench too slowly and precipitation began prematurely. Cool too fast and internal stresses developed. German metallurgists had worked out these parameters through years of systematic research. Harris had to rediscover them in months. By October 1917, Harris had established working parameters for producing American duralumin. Alcoa designated the alloy 17S, the 17th aluminum alloy in their experimental series. Initial production began in November. Quality was inconsistent. Some batches achieved German equivalent properties. Others fell short. The problem was scaling laboratory procedures to factory conditions. Heat treatment furnaces in production facilities couldn't maintain the temperature uniformity of laboratory equipment. Quenching tanks cooled unevenly. Workers lacked experience with the new material. Harris spent the winter of 1917 and 1918 shuttling between New Kensington and production facilities, troubleshooting problems, refining procedures. The pressure was immense. American aircraft production was ramping up. Factories needed materials. Every delay meant fewer planes reaching France. Harris worked 16-hour days, sleeping on a cot in his laboratory. His health deteriorated. His wife, back in Pittsburgh, saw him only on occasional weekends. But gradually, production improved. By spring 1918, Alcoa was shipping consistent, high-quality 17S aluminum in quantity. The technical achievement was remarkable. In less than a year, Harris had reverse-engineered a material that Germany had spent a decade developing. But the war's end came before American 17S could significantly impact combat. The armistice of November 1918 found American aviation still largely equipped with European-designed aircraft. The vast fleets of American-designed, American-built warplanes never materialized. This apparent failure obscured a crucial success. American industry now understood age-hardening aluminum. Alcoa had production capacity for aviation-grade alloys. The knowledge would compound over the following decades. Raymond Harris continued metallurgical research through the 1920s. He developed improved alloys, refined heat treatment procedures, and trained a generation of aluminum metallurgists. The 17S alloy evolved into 2017 with optimized composition and processing. By 1930, American aluminum metallurgy had not only caught up with Germany, but surpassed it. Harris's key insight was understanding precipitation hardening at a fundamental level. German metallurgists had discovered age hardening empirically, but never fully understood the mechanism. They knew what worked, but not why. Harris and his colleagues at Alcoa developed theoretical models explaining how precipitates formed, why they strengthened aluminum, and how processing variables affected results. This theoretical understanding enabled systematic improvement. Instead of trial and error, American metallurgists could predict how composition changes would affect properties. They designed new alloys for specific applications, high strength for structural components, improved corrosion resistance for marine applications, better formability for complex shapes, heat resistance for engine components. In 1931, Alcoa introduced 24S, later designated 2024, an alloy optimized for aircraft structures. The new alloy achieved higher strength than 17S while maintaining good fatigue resistance, critical for aircraft that experienced millions of stress cycles during service. The Douglas DC-3, introduced in 1936, used 24S extensively. So did the Boeing 247 and Lockheed Electra. American commercial aviation entered the aluminum age. While American metallurgists advanced aluminum technology, the aircraft industry was transforming. In 1927, Charles Lindbergh crossed the Atlantic in the Spirit of St. Louis, a fabric-covered monoplane. By 1937, the Douglas DC-3 was carrying passengers across America in all-metal aircraft. The transition happened because aluminum alloys had matured. Designers could now specify materials confident in their properties. Manufacturers could source consistent, high-quality aluminum. Airlines could operate metal aircraft knowing they would withstand years of service. When war returned to Europe in 1939, American aircraft manufacturers were ready. Boeing was producing B-17 Flying Fortress bombers, all-metal four-engine aircraft that would eventually bomb Germany into submission. Consolidated was developing the B-24 Liberator, even more dependent on aluminum structures. Douglas, Lockheed, North American, and Curtiss were tooling up for massive production. All required aluminum. Lots of aluminum. American aluminum production in 1939 totaled approximately 327,000 tons. By 1943, production exceeded 1.8 million tons. The expansion required new smelting plants, new power sources, new bauxite mines. But it also required new alloys, improved processing, better quality control. Raymond Harris, now leading Alcoa's research division, oversaw metallurgical development supporting the expansion. The challenge wasn't just producing more aluminum, it was producing aluminum with consistent properties at unprecedented scale. A bomber like the B-24 contained approximately 360,000 individual parts, many aluminum. Every sheet, every extrusion, every forging had to meet specifications. Variation that might be acceptable in peacetime production became unacceptable when aircraft were being shot at. Harris's team developed statistical quality control methods for aluminum production. They established standardized testing procedures. They trained inspectors at plants across the country. They created alloy specifications that any qualified manufacturer could follow. The result? was an industrial system capable of producing millions of tons of aviation-quality aluminum with remarkable consistency. Germany faced different challenges. German aluminum production in 1939 was actually higher than American production, about 339,000 tons versus 327,000. German metallurgists were excellent, heirs to the tradition that had produced Duralumin. But Germany lacked bauxite. The country depended on imports from Hungary, France, and Yugoslavia, sources that became increasingly uncertain as the war progressed. More critically, Germany lacked electricity. Aluminum smelting requires enormous amounts of electrical power, approximately 15,000 kilowatt-hours per ton of aluminum produced. American aluminum plants in the Pacific Northwest drew power from massive hydroelectric dams on the Columbia River, cheap and abundant. German plants relied on coal-fired power stations, competing for coal with steel mills, railroads, and residential heating. By 1943, German aluminum production had peaked at around 250,000 tons. American production was approaching 1.5 million tons. The gap would only widen. Albert Speer, German armaments minister, recognized the disparity. He prioritized aluminum allocation for aircraft production, diverting supplies from other uses. But arithmetic was inexorable. Germany couldn't produce enough aluminum to match American aircraft output, regardless of how efficiently it was allocated. The strategic consequences were devastating for Germany. By 1944, American factories were producing aircraft faster than the Luftwaffe could shoot them down. For every B-17 lost over Germany, 2 replacements rolled off Boeing's production lines. For every Focke-Wulf 190 that fell to American guns, Germany struggled to produce 1 replacement. The attrition rates that seemed catastrophic to American planners, 60 bombers lost over Schweinfurt, were actually sustainable losses for an industry producing 50,000 aircraft per year. Germany couldn't sustain equivalent losses because Germany couldn't produce equivalent numbers. The aluminum advantage was invisible to casual observers. Headlines celebrated bombing raids and fighter aces. Newsreels showed aircraft factories without explaining the metallurgical infrastructure that made them possible. But logistics officers understood. Without aluminum, aircraft were impossible. Without adequate aluminum production, air superiority was impossible. Without air superiority, victory was impossible. Raymond Harris received the Medal for Merit in 1946 for his wartime contributions. The citation praised his development of aluminum alloys, critical to aircraft production. He returned to peacetime research, continuing to advance aluminum metallurgy until his retirement in 1954. He died in 1967, remembered by colleagues as brilliant but modest, a man who preferred laboratory work to public recognition. The physics that made age-hardening work remained unchanged from Harris's discovery. The process exploits fundamental metallurgical principles. When aluminum is heated to approximately 500 degrees Celsius, copper atoms dissolve into the aluminum crystal structure, forming a solid solution. If the alloy is then quenched rapidly, copper atoms remain trapped in positions they would not occupy at room temperature. The solid solution is supersaturated, unstable. Over time, copper atoms migrate through the aluminum lattice, clustering together and eventually forming precipitates, tiny particles of copper-aluminum compound dispersed throughout the material. These precipitates impede dislocation movement. Dislocations are defects in the crystal structure that allow metals to deform. When precipitates block dislocations, the material becomes harder and stronger. The size and distribution of precipitates determine final properties. Very small precipitates, formed during early aging stages, provide moderate strengthening. Optimal precipitates, formed after several days at room temperature, provide maximum strength. Overly large precipitates, formed during extended aging or elevated temperature exposure, actually reduce strength. Understanding these relationships allowed Harris and subsequent metallurgists to design heat treatment schedules producing desired properties. Temperature control during solution treatment is critical. Too low and insufficient copper dissolves. Too high and the material approaches its melting point, risking grain boundary melting and permanent damage. The window is narrow, perhaps 20 degrees Celsius. Maintaining this window across large production furnaces required careful engineering and constant monitoring. Quenching rate affects precipitate distribution. Faster quenching retains more supersaturation, enabling greater eventual strength. But faster quenching also induces thermal stresses that can distort parts. Designers had to balance strength requirements against dimensional tolerances, selecting quenching procedures appropriate for each application. Aging temperature and time provide additional control. Room temperature aging, natural aging, produces maximum strength over several days. Elevated temperature aging, artificial aging, produces slightly lower strength but faster, useful for production scheduling. Some alloys respond to two-stage aging treatments, combining different temperatures for optimized properties. The complexity of these relationships explains why Germany's early lead in Duralumin didn't translate into permanent advantage. German metallurgists had discovered age hardening empirically, but lacked theoretical framework for optimization. American metallurgists, starting later but approaching the problem scientifically, developed superior understanding that enabled superior alloys. By 1945, American aluminum alloy technology had far surpassed German achievements. Alloys like 7075, developed during the war, achieved tensile strengths exceeding 80,000 pounds per square inch, roughly twice the strength of original Duralumin. Post-war aircraft like the Boeing B-52 and Lockheed C-130 used these advanced alloys extensively, achieving performance impossible with earlier materials. The legacy extended beyond military aviation. Commercial aircraft like the Boeing 707, introduced in 1958, relied on aluminum alloys developed from wartime research. The 747, 767, and subsequent Boeing aircraft continued the tradition. Even the Airbus A380, first flown in 2005, used aluminum alloys descended from Raymond Harris's 17S. When composite materials began displacing aluminum in some applications during the 1980s and 1990s, aluminum metallurgists responded with further improvements. Aluminum-lithium alloys achieved lower density than conventional aluminum. Advanced processing techniques produced materials with improved fatigue resistance. The Boeing 787, though primarily composite, still uses aluminum alloys for significant portions of its structure. Modern aluminum alloys trace their lineage directly to discoveries made in American laboratories during 1917 and 1918. The age-hardening mechanism Harris elucidated remains fundamental to high-strength aluminum. The processing techniques his team developed evolved but were never replaced. The industrial infrastructure built to support wartime production became the foundation for post-war aluminum industry expansion. The irony isn't lost on historians. Germany invented Duralumin. German metallurgists pioneered aircraft aluminum. German industry produced the first all-metal combat aircraft, but German secrecy, intended to preserve advantage, ultimately failed. Forced to reinvent Duralumin, American metallurgists didn't just duplicate German achievements, they surpassed them. The student exceeded the teacher precisely because the teacher refused to share knowledge. The comparison between aluminum and ball bearings illuminates different paths to industrial advantage. Germany's ball bearing production was concentrated in a few vulnerable facilities, especially Schweinfurt. Allied bombers attacked those facilities at terrible cost, ultimately achieving limited results because German production dispersed and stockpiles buffered shortages. American aluminum production, by contrast, was geographically dispersed from the start. Smelters in the Pacific Northwest exploited Columbia River hydropower. Plants in the Gulf Coast region used natural gas. Facilities in the Ohio Valley drew on regional coal supplies. No single bombing campaign could cripple American aluminum production. This dispersal wasn't strategic foresight. It reflected the distribution of electrical power, the fundamental input for aluminum smelting. But the result was strategic advantage. American aluminum production was essentially immune to attack, whether by bombing or submarine interdiction. Raw materials came from domestic bauxite deposits in Arkansas and from secure Caribbean sources. Power came from American generators burning American coal or harnessing American rivers. Germany faced the opposite situation. German aluminum smelters concentrated near power sources that were themselves vulnerable. Bauxite imports depended on transportation networks subject to disruption. As Allied bombing intensified and transportation collapsed during 1944 and 1945, German aluminum production fell despite theoretically adequate smelting capacity. The structural differences between American and German industrial organization proved decisive. German industry had pioneered many technologies, including Duralumin, but German industrial structure, concentrated and dependent on imports, couldn't sustain production under wartime conditions. American industrial structure, dispersed and self-sufficient, could. Raymond Harris didn't design American industrial structure, he just solved a metallurgical problem. But his solution fit into a larger system that converted metallurgical knowledge into manufactured aircraft at unprecedented scale. The system included not just metallurgists, but mining engineers, electrical engineers, production managers, quality inspectors, transportation specialists, and countless others. Each contributed essential elements. None could have succeeded alone. This systemic quality distinguished American wartime production. Individual innovations mattered, but their integration into functioning systems mattered more. German engineers produced numerous brilliant innovations during the war: jet engines, guided missiles, advanced submarines. But German industry couldn't produce these innovations in quantity. American innovations were less dramatic, but produced in enormous quantity. Quantity, not technical sophistication, won the war. The same principle applied to aluminum. German Duralumin was technically excellent. American 17S and 24S were technically adequate, but American production exceeded German production by factors of 3, 4, eventually 6. The resulting aircraft, though individually no better than German designs, overwhelmed German defenses through sheer numbers. Today, aluminum remains essential to aerospace. Modern alloys achieve properties Harris couldn't have imagined. Manufacturing techniques have evolved dramatically. But the fundamental metallurgy, age-hardening aluminum alloys, exploiting precipitate strengthening, remains unchanged from 1917. Every commercial aircraft flying today uses materials descended from Raymond Harris's laboratory work. The story rarely appears in history books. No dramatic moments mark the narrative. No photographs capture metallurgists peering at heat treatment furnaces. No generals credited aluminum production for victory. But without the metallurgical foundations laid in 1917 and 1918, the aircraft that won World War II would have been impossible. When American bombers appeared over Germany in 1943, their aluminum skins gleaming in the sunlight, they represented not just manufacturing capacity, but metallurgical knowledge. Each aircraft was a statement that America had mastered aluminum, had scaled that mastery to industrial proportions, and could sustain aircraft production that Germany couldn't match. Henry Kaiser received credit for Liberty ships. Andrew Higgins received credit for landing craft. William Knudsen received credit for coordinating war production. Raymond Harris received a medal and faded into obscurity. His contribution was too technical, too invisible, too distant from combat to attract attention. But every B-17 that flew, every P-51 that fought, every C-47 that delivered supplies used aluminum that Harris had learned to produce. The hundreds of thousands of aircraft that America built during World War II, each one represented his metallurgical achievement multiplied by industrial power. The mathematics of that multiplication made the difference between victory and defeat. In April 1917, America had no aviation aluminum. By April 1945, America had produced more aircraft than all other combatants combined. The transformation took less than 3 decades, driven by engineers who solved technical problems without expecting historical recognition. Raymond Harris was one of those engineers. He didn't invent age-hardening aluminum. Alfred Wilm did that. But he made it American, made it producible at scale, made it the foundation for aircraft production that changed history. His laboratory in New Kensington, Pennsylvania, contributed as much to victory as any battlefield. The tapered roller bearing and the age-hardened aluminum alloy share a common lesson. Wars are won not just by soldiers, but by engineers. Not just by courage, but by metallurgy. Not just by strategy, but by production. The nations that master these industrial fundamentals, the boring technical details that determine whether machines work, gain advantages that no amount of tactical brilliance can overcome. Germany learned this lesson too late. America learned it just in time. If you found this story of hidden industrial history interesting, leave a comment telling us which forgotten engineering achievement you would like us to explore next. And if you haven't already, consider subscribing so you don't miss our next investigation into the technical foundations of victory.